Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about a module Schrodinger Picture and Time Evolution Operator from the paper Quantum Mechanics 1. So in this module we shall be studying and we shall be able to know about the Schrodinger picture. We will also learn the important properties of time evolution operator. We will then derive the expressions for the equations of motion for dynamical observables in the Schrodinger picture. Then we will get to learn the properties of a propagator and know how to derive the equation satisfied by it. Finally, we'll also get to know the similarity between the equations of motion in quantum mechanics and those that occur in classical mechanics. The main objective of non-relativistic quantum dynamics is to determine the variables or parameters that specify the state of a physical system, and secondly, to describe the time evolution of the system. While there are many possible representations of the wave functions and observables connected by unitary transformations, it is useful to identify certain classes of representations called pictures which differ in the way the time evolution of the system is developed. In this module, starting from time-dependent Schrodinger equation, we shall study how the state of an arbitrary time is determined from a given initial state through the time evolution operator and learn the basic properties of this operator. In the Schrodinger picture, where the dynamical variables are time independent, we shall then set up the equations of motion involving the evolution in time of the expectation values of the corresponding Hermitian operators. We shall also study the properties of the propagator and derive the equation satisfied by it. Finally, we will point out that the correspondence and the similarity of the equations of motion for the expectation values of the operators in quantum mechanics and those of dynamical variables in classical mechanics. Time variation of expectation values. Now, in this equation, the above equation that we were just discussing, the operator h as a function of time t is called the generator of the infinitesimal unitary transformation, and hence we can rewrite the above equation as the state vector psi as a function of time t plus dt is equal to the evolution operator u as a function of time t plus dt and time t acting on the state vector psi as a function of time t, and comparing this equation using the evolution operator with the equation discussed earlier, which was using the Hamiltonian operator h as a function of time t, also called the generator of the infinitesimal unitary transformation, we have the evolution operator u as a function of time t plus dt and time t is equal to bracket open unit operator minus iota by h cross whole times Hamiltonian operator h as a function of time t times dt, where the evolution operator u as a function of time t plus dt and time t is called the infinitesimal evolution operator. Now, since the Hamiltonian operator is Hermitian, therefore it requires that the infinitesimal evolution operator u as a function of time t plus dt and time t is unitary. Thus, in general, one can say that the evolution operator u as a function of time t and time t prime is also unitary. And we have the general equation for the evolution operator given as evolution operator u as a function of time t prime and time t is equal to the inverse of the evolution operator u as a function of time t and time t prime is equal to evolution operator u dagger as a function of time t and time t prime, which basically establishes that the evolution operator u is unitary. Now, the time variation of the expectation values. In order to calculate the time variation of the expectation values, the rate of change of the expectation value of an operator A of the observable A is given by time derivative of the expectation value of operator A is equal to time derivative of bra vector psi operator A ket vector psi, and then this can further be expanded as bra vector partial time derivative of the wave function psi operator A acting on ket vector psi plus bra vector psi partial time derivative of operator A acting on ket vector psi plus bra vector psi operator A acting on partial time derivative of ket vector psi. Schrodinger picture. State vector and the expectation value of the Hermitian operator corresponding to the dynamical variable. The equations of motion should therefore involve the evolution in time of these expectation values. Now, the variation with time of the expectation value, which is the expectation value of the operator A, is equivalent to bra vector psi operator A acting on ket vector psi, can be viewed as arising from when 1. The state vector changes with time but the operator A does not, and 2. When the operator A changes with time but the state vector psi does not. So corresponding to the point 1 that we just discussed, we get the Schrodinger picture, while in the second point that we discussed, we get the Heisenberg picture. Thus, in the Schrodinger picture, operators corresponding to observables like position, momentum, kinetic energy are time independent, but state vectors depend on time. Now, using the time dependent Schrodinger equation for replacing the time derivative terms in the above equation, we can rewrite the result as time derivative of the expectation value of operator A is equal to 1 upon minus iota times h cross whole times expectation value of the operator A in terms of the Hamiltonian operator h, wave function psi, and the wave vector psi, that is bra vector Hamiltonian operator h, wave function psi, operator A ket vector psi plus bra vector psi partial derivative with respect to time of operator A ket vector psi plus 1 upon iota times h cross whole times bra vector psi operator A operator h acting on ket vector psi. Now, since the Hamiltonian operator is Hermitian, therefore the first matrix element of the above equation on the left hand side can be written as bra vector psi operator h operator A acting on ket vector psi, and thus we can rewrite the above equation as time derivative of the expectation value of operator A is equal to 1 upon iota times h cross whole times expectation value of the commutation relation of the operator A with operator h plus the expectation value of the partial time derivative of the operator A, which is written as bra vector psi partial derivative with respect to time of operator A ket vector psi, where the expectation value of the commutation relation of operator A and operator H is given as bra vector psi operator A operator H minus operator H operator A ket vector psi. So basically one has just expanded the commutation relation over here to express it in terms of the state vector psi. Now if the operator A does not depend on time explicitly, so that the partial derivative with respect to time of the operator A goes to 0, then we have the time derivative of the expectation value of operator A as given by only the first term of the above equation, that is 1 upon iota times h cross whole times the expectation value of the commutation relation of the operator A with operator H. Now, if the Hamiltonian operator H commutes with the operator A, then its expectation value does not depend on time, because the time derivative of the expectation value of the operator A in such a case will turn out to be 0. The observable A is then said to be a constant of motion, that is, that it does not depend on time. Constant of motion, a Hamiltonian. Now let us consider the example of time independent Hamiltonian. That means that the Hamiltonian operator does not explicitly depend on time. Suppose we have chosen a time independent Hamiltonian operator such that the partial time derivative of the Hamiltonian operator H is equal to 0. Then, substituting the Hamiltonian operator H for the operator A in the above equation which defined the operator A, we finally have that the time derivative of the expectation value of the Hamiltonian operator is equal to 1 upon iota times h cross whole times the expectation value of the commutation relation of the Hamiltonian operator with itself, and this turns out to be equal to 0, thus implying that the Hamiltonian or the total energy E of the system is a constant of motion. So what this means is that as the time changes, the energy associated with the physical system does not change but remains constant. Hence, for a particle which is moving in a time-independent potential, that is a potential energy which is independent of time, or rather does not change with time, it is easy to verify that the Schrodinger equation will have the solution of the form given by the wave function psi as a function of position vector r and time t is equal to u as a function of position vector r times f as a function of time t. That means we can do a separation of variable of the total wave function psi as a function of position vector r and time t into a product of two functions, one which is purely a function of the position vector r and the other which is a function of purely time. And the Schrodinger equation in this case can then be written as iota times h cross times partial derivative with respect to time of the wave function psi as a function of position vector r and time t is equal to the Hamiltonian operator acting on the wave function psi as a function of position vector r and time t, and this is equal to the energy eigenvalue of the physical system times the wave function as a function of position vector r and time t. This time dependent Schrodinger equation can be written using the separation of variable of the above wave function as iota times h cross times time derivative of the function f with respect to time t is equal to the energy eigenvalue of the function f with respect to time t, and minus h cross square by twice m times del square plus potential energy operator v as a function of position vector r whole acting on the wave function u as a function of position vector r is equal to the energy eigenvalue E as a times the function u as a function of position vector r. So in this manner one sees that one can have two separate equations, one corresponding to only the time dependent part of the wave function and the other corresponding to only the position dependent part of the wave function. The first equation shows that the time dependent part of the wave function, that is the function f as a function of time t, is proportional to exponential to the power minus iota times energy eigenvalue e times time t upon h cross, and the total wave function psi as a function of position vector r and time t can be written as u function as a function ue as a function of position vector r times e to the power or exponential to the power minus iota times energy eigenvalue e times time t upon h cross, where the function ue as a function of position vector r are the eigenfunctions of the energy E for the time independent Hamiltonian corresponding to energy E. Existence of a propagator. We notice that the expectation values of the operators obey the same equations of motion in quantum mechanics as the dynamical variables obey the equations of motion in classical mechanics. That means that the role that the operators play in the equation of motion as defined in quantum mechanics is the same as that played by the dynamical variables in the equations of motion written in the classical mechanics formalism. And this equivalence is there provided that one can identify the expectation value of 1 by iota times h cross whole times the commutation relation between operator A and operator B as going to the classical mechanical formalism of the Poisson's bracket of the dynamical variable A and dynamical variable B. Now let us discuss the existence of a propagator. So using the time evolution operator, it is possible that one can directly link the states of the physical system at two different times, and one can write the state of the physical system at some later time t2 given by k vector psi as a function of time t2 is equal to time evolution operator u as a function of time t2 time t1 acting on ket vector psi as a function of time t1, or the wave function psi as a function of position vector r2 and time t2 is equal to the volume integral over vector dr1 of the bra vector r2 time evolution operator u as a function of time t2 and t1 acting on ket vector r1 bra vector r1 acting on the ket vector psi as a function of time t1, and this can then be written as volume integral over vector dr1 bra vector r2 time evolution operator u as a function of time t2 and time t1 acting on ket vector psi as a function of position vector r1 and time t1. Here we have used the closure property for the state vector r1. Now on looking at this equation, one can identify the bra vector r2 time evolution operator u as a function of time t2 and time t1 acting on ket vector r1 is equal to some operator k as a function of position vector r2 at time t2 and position vector r1 and time t1, where we are assuming that the time t2 is greater than time t1, that is time t2 occurs at a later instant than time t1, so that this function k goes to 0 for any time t2 which is less than time t1, and we can define this function k as a function of position vector r2 and time t2 and position vector r1 time t1 as being equal to bra vector r2 time evolution operator u as a function of time t2 and time t1 ket vector r1 whole times theta as a function of time t2 minus time t1, where the function theta as a function of time t2 minus t1 is a step function. Slide 13. Equation of a propagator. Now the function k as a function of position vector r2 at time t2 and position vector r1 and time t1 can be written as in a compact form as function k as a function of 2, 1, and this represents the probability amplitude that the particle starting from the point r2, that is the position vector r2 at time t2, arrives at the position vector r1 at time t1. Thus, the Hamiltonian of the system does not explicitly depend on time, so we can write the Hamiltonian operator H acting on the time evolution operator Un is equal to the energy eigenvalue En acting on the operator Un. So the Hamiltonian operator H acting on the state vector Un is equal to the energy eigenvalue En times the state vector Un in such a case where the Hamiltonian operator does not explicitly depend on time. And then the equation of motion can be written as in terms of the time dependent Schrodinger equation as iota times h cross whole times partial time derivative of the time evolution operator u as a function of time t and time t naught is equal to Hamiltonian operator h as a function of time evolution operator u as a function of time t and time t naught, and this can be integrated to give us the final expression for the time evolution operator u as a function of time t2 and t1 as equal to exponential to the power minus iota times Hamiltonian operator h times t2 minus t1 upon h cross, and this can then further be expressed as time evolution operator u as a function of time t2 and time t1 is equal to summation over exponential to the power iota times energy eigenvalue En times within brackets t2 minus t1 upon h cross whole times the closure relation of the state vector Un, that is ket vector Un, bra vector Un. And here we have used the closure property of the vector state vector Un, where the function Un as a function of position vector r2 times exponential to the power minus iota times energy eigenvalue En times t2 upon h cross is a solution of bracket open iota times h cross times partial derivative with respect to time t2 minus Hamiltonian operator acting on within brackets position vector r2 minus iota times h cross del operator 2 whole bracket close acting on the function Un as a function of position vector r2 times exponential to the power minus iota times energy eigenvalue En times time t upon h cross, this whole being equal to 0. So the equation of the propagator K21 is obtained as bracket open iota times h cross times partial derivative with respect to time t2 minus Hamiltonian operator h as a function of position vector r2 and minus iota times h cross del operator 2 bracket close whole acting on the propagator function k as a function of position vector r2 and time t2 and position vector r1 time t1, and this is equal to iota times h cross times delta function of t2 minus t1 whole times summation over n function un star as a function of position vector r1 function un as a function of position vector r2 times exponential to the power minus iota times energy eigenvalue En times within brackets t2 minus t1 by h cross. Schrodinger picture. Now, according to the postulate of quantum mechanics, the state of a physical system at any given instant in time, that is at any fixed time t naught, is represented by the ket vector psi as a function of t naught. Thus, the initial state of a physical system is denoted by the ket vector psi t naught, and the state of the system at any subsequent time t equal to t given by the ket vector psi t is determined by the time-dependent Schrodinger equation, which can be written as iota times h cross times time derivative of the state vector psi t or the ket vector psi t is equal to Hamiltonian operator acting on the ket vector psi t, that is the ket vector psi as a function of time t. Since this is a linear equation, hence it is clear that the correspondence between the initial state of the physical system denoted by the ket vector psi as a function of t naught and the state of the physical system at some later instant in time t denoted by the ket vector psi as a function of t is also linear. That is, the state vector, that is the ket vector psi as a function of t naught is equal to lambda 1 times ket vector psi 1 as a function of t naught plus lambda 2 times ket vector psi 2 as a function of t naught, where the ket vector psi 1 as a function of t naught and the ket vector psi 2 as a function of t naught are the two wave function solutions or the states representing the physical system, and lambda 1 and lambda 2 are the corresponding linear multiplying factors for the two wave functions psi 1 and psi 2 respectively. In a similar manner, in order to define the state of the physical system at some later instant in time t equal to t, the ket vector psi as a function of time t can also be written as lambda 1 times ket vector psi 1 as a function of time t plus lambda 2 times ket vector psi 2 as a function of time t, where lambda 1 and lambda 2 are complex constants corresponding to the wave functions psi 1 as a function of t and psi 2 as a function of t respectively. Similarity of equations of motion. Similarity between equations of motion in quantum mechanics and those in classical mechanics. In the presence of an external field, the operator A may depend explicitly on time. In that case, we will have to consider the general equation. Here, it is interesting to recall the equation of motion we encounter for the dynamical variable A in classical mechanics. That is, the time derivative of the operator A is equal to the partial time derivative of the operator A plus the Poisson's bracket of the operator A with the Hamiltonian operator, where Poisson's bracket, that is the curly bracket of operator A and the Hamiltonian operator, is defined as the Poisson's bracket of operator A and the Hamiltonian operator is equal to summation over I bracket open partial derivative with respect to Qi of the operator A times partial derivative with respect to Pi of the operator H minus partial derivative with respect to the Qi coordinate of the operator H times partial derivative with respect to the coordinate Pi of the operator A, where the coordinate Qi and the coordinate Pi are the generalized coordinates or the normal coordinates in the classical picture, and this Poisson's bracket obeys the property that Poisson's bracket of operator A with operator B is equal to minus of the Poisson's bracket of operator B with operator A. And as mentioned earlier, Qi and Pi are the generalized coordinates and momenta, where the Poisson's bracket of the momenta coordinate Pi and the generalized coordinate Qi is equal to delta function ij, where delta function ij is equal to 0 for I not equal to j, and delta function ij is equal to 1 for I equal to j. Of t, we can define a linear operator or rather we can define the existence of a linear operator u as a function of time t and time t0 called the evolution operator, such that the ket vector psi as a function of time t, denoting the state of the physical system at some time t, is equal to the operator u as a function of time t and time t0 acting on the ket vector psi as a function of time t0. From this equation, it is clear that the operator u as a function of time t and time t0 is equal to a unit operator. Also, by substituting this relation in the time-dependent Schrodinger equation, we have iota times h cross times time partial derivative of with respect to time of the evolution operator u as a function of time t and time t0 acting on the state vector or the ket vector psi as a function of time t0, and this turns out to be equal to Hamiltonian operator h as a function of time t acting on the evolution operator u as a function of time t and time t0 acting on the ket vector psi as a function of time t0. For any arbitrary state vector or ket vector psi as a function of time t0 defining the state of the physical system at time t0, we can thus write iota times h cross times partial derivative with respect to time of the evolution operator u as a function of time t and time t0 is equal to Hamiltonian operator h as a function of time t acting on the evolution operator u as a function of time t and time t0. This first order differential equation in time t along with the initial condition determines completely the evolution operator u as a function of time t and time t0. And by integrating the above equation with respect to time and using the initial condition that we've defined earlier, we finally get the value of the evolution operator as the evolution operator u as a function of time t and time t0 is equal to unit operator minus iota by h cross whole times the integration over time dt prime with limits from t0 to time t on the Hamiltonian operator h as a function of time t prime acting on the evolution operator u as a function of time t prime and t0. A vector psi as a function of time t0, ket vector psi as a function of time t0. That means that the probability density function of the wave function psi at some time t should be equal to the probability density function of the wave function psi at time t0 for the probability density to be conserved. And this gives us the relation bra vector psi as a function of time t, ket vector psi as a function of time t can be expanded in terms of their relation using the initial state ket vector psi as a function of time t0 and the evolution operator u as a function of time t and t0, and is given by the mathematical relation as the probability or the bra vector of the operator u acting as a function of time t and t0 acting on state vector psi as a function of t0, ket vector operator u as a function of time t and t0 acting on state vector psi as a function of t0, and this turns out to be equal to the expectation value of the evolution operator and is given by bra vector psi as a function of t0, evolution operator u dagger as a function of time t and time t0, evolution operator u as a function of time t and time t0 acting on ket vector psi as a function of t0. Now, the normalization condition demands that the product of the evolution operator u dagger as a function of time t and time t0 and evolution operator u as a function of time t and t0 be equal to the unit operator. And this result we get because of the conservation of the probability density. Thus, in order to ensure that the evolution operator U is unitary, one can do this exercise to show that the evolution operator U as a function of time t and time t naught acting on the evolution operator U dagger as a function of time t and t naught is equal to unit operator. Now let us calculate the evolution operator between the instants at time t equal to t and at time t equal to t plus dt. For this, we write the Schrodinger equation as d, that is the derivative of the state vector psi as a function of time t, is equal to the state vector psi as a function of time t plus dt minus the state vector psi as a function of time t, and this is equal to minus iota by h cross whole times the Hamiltonian operator h acting on the state vector psi as a function of time t whole times dt, and this can then be written as the state vector psi as a function of time t plus dt is equal to bracket open unit operator minus iota times by h cross Hamiltonian operator h as a function of time t times dt bracket close acting on the state vector psi as a function of time t. So students, let us now summarize what we have learned in this module. Firstly, we learned about the Schrodinger picture, and we also understood how the Schrodinger picture is different from the Heisenberg picture in terms of the time dependence of the operators vis-a-vis the time dependence of the state vectors. Then we derived the expression for the equations of motion for dynamical observables in the Schrodinger equation, and we also learned how we can set up these equations of motion for different dynamical observables. After that, we also learned the properties of a propagator and how we can use these properties and how to derive the equations satisfied by it. We also learned the similarity between the equations of motion in quantum mechanics and those in classical mechanics. And having understood this similarity, then we actually found out that the operators as defined in quantum mechanics are the quantum counterpart of the corresponding physical quantities that we define in classical mechanics. Thank you.